Okay. Yeah, what can I say? Well, of course, I don't know if you know, I'm from Mexico. I finished my PhD there around 2016, 15. Ever since I've been working in these topics of kind of supergravity and maybe CFT stuff. Yeah, well, after I finished my PhD in Mexico, I moved to Swansea University. That was my first postdoc. And then, yeah, after that, I moved to Shanghai Yatong University. That was the second, and actually, this is the third one, so I'm very happy to be here. And yeah, all this time, I mean, the topics I've been working are related to mostly related to the thing I will discuss today, among other stuff, but it is all around dualities, you know. So yeah, this is something I can say. Hopefully after the talk it will become clear what is the thing in which I'm doing, things I'm working, and yeah, we can discuss about it. Okay. Sorry, can you hear me?
Yes. Yes.
Okay, just because at some point I don't know. If you can hear me, then I can continue, because at some point I thought I was mute, but anyway.
No, it was fine. There was
Okay.
just maybe some feedback noise, but I don't know if it was from you, but it's okay now.
Okay.
Maybe that's from France, if he's in the same room.
Yeah, because yeah, maybe he's just next to me, so maybe the echo.
No, it's okay now. So.
Okay, so anyway, but the first part was not important, so now we can move to the important thing, I suppose. And yeah, as I said, yeah, this is a part of what I'm gonna discuss today is part of the work I've been doing basically for the last years in different lines, but basically this is it's been around all these ideas of deformations and applications to AdS3 N. So shall I start?
Yes.
Okay, cool. So yeah, as the title says, I'll be discussing marginal deformations of AdS3 backgrounds preserving 0-4 supersymmetry. And yeah, here is an outline of the talk. First, I'll introduce these AdS3 solutions that we will use as seed solutions, discuss some properties of them. And then I'll move to the deformations of these solutions in 10 and 11 dimensional supergravity. And after having these backgrounds, I'll study some observables that characterize these solutions. And also I'll discuss the issue of supersymmetries preserved after the deformation. And finally, if time allows, I'll discuss some field theory stuff related to these ideas. So the still is work in progress, but if time allows, I'll say some stuff about this. So, yeah, as I said before, I'll be discussing the AdS3 solutions that I will use here as seed backgrounds that we will later deform. And just before to go into details of these specific backgrounds, one might wonder what can we expect from these backgrounds, meaning by looking at the symmetries of the solutions, what can we expect the form of these solutions will look like. And so for sure, the metric we have here, the metric must have an AdS3 factor. And here I'm allowing for generality to have a non-trivial warping, that this non-trivial warping will depend in general of the 7-dimensional internal space transverse to AdS3. And of course, in general, we'll have non-trivial dilaton, NS3 flux, and Ramon fluxes. But we can say more because we are working with solutions that we want them to preserve 0-4 supersymmetry. And in here, I underline the word small, because small 0-4 supersymmetry implies that the R-char symmetry is SU2. And then as such, we must realize this symmetry geometrically. And the simplest way to do that is just to put a sphere on the solution. And so,
can I ask more about what small means? I mean, is it in the sense that it's constant on the boundary, or
what is
big?
Yeah, this has to be with you know, for this kind of theories. For instance, you have in two-dimensional, the superconformal algebra can have, for instance, for these 0-4 theories, is SU2 times SU2. So whenever you talk about large and small super algebra, is large is whenever you have the SU2 or the R symmetry to be SU2 times SU2. Mm-hmm. And the small super algebra is such that the R symmetry is SU2, but it's small and large in that sense.
Okay.
Okay. So yeah, as I was discussing, so the 7-dimensional space then decomposes in this form. We will have this S2 factor. And once again, we allow for a non-trivial warping here, where this warping and this one will depend trivially on the 5-dimensional space. And so this is all what we can say about these solutions, but a complete classifications of these kind of solutions whenever this 5-dimensional space here supports an SU2 structure was obtained by Yolanda Lozano, McPherson, Carlos Núñez, and Nayeli Ramirez. And actually they found two classes of solutions. And in here I will just focus in one of them, that is class 1 solutions. But for both solutions, these basically this 5-dimensional space decomposes in terms of a 4-dimensional submanifold times an interval. And for class 1 solution, the 4-dimensional submanifold is Calabi-Yau. And then for simplicity, from now on, I will take that Calabi-Yau space to be T4. And so, yeah.
So, I mean, it can only be T4 or K3.
Yeah, exactly. But yeah, I mean, the other option is to take K3. But in here, in order for us to, in order for me to use the deformation I would use, we need the knowledge of the metric explicitly. So okay. Yeah, for that reason. But you can also take K3. So yeah, the explicit form of the solution, as I said, when this 5-dimensional space has this SU2 structure, is given by this expression. This is the NS sector, which is rather non-trivial. And of course, we also have a non-trivial Ramon fluxes here. In here, I just wrote down the lower dimensional Ramon fluxes because using the relation by Hodge duality, we can get the higher dimensional ones. Notice here that this solution is in type 2A and also is in massive type 2A because we have non-zero Romans massing here. And so, yeah, the important thing of these solutions is that they, regardless the very complicated, the way they look, they are very simple and they are parameterized in terms of 3 functions, U, H4, and HA. And supersymmetry, together with the Bianchi identities, implies that they have to satisfy these 3 conditions, which means that these functions has to be order 1 polynomials, roughly. And this is true, or this must be true just away from localized sources. And one extra comment regarding these solutions is that we typically ask the 5-dimensional space of the 5-dimensional piece to be of compact size. Whenever we have in mind the interplay of these solutions with AdS3 N, better to have an internal compact space. In here, we know T4 is compact, but rho is just an interval that can take, can be semi-infinity or stuff like that. So, but in here, we will use these functions H4 and HA in order to bound this rho interval. And to be more concrete, here is a choice of these global solutions, the choice for these functions here. We have they are defined in terms of these constants, mu, nu, alpha, and beta, which they are not totally random, and they are not totally arbitrary constant because we'll see later on they have some precise physical meaning. And just to be more concrete, here it is a profile of one of these H functions. As you see in here, the U function has the same value through all the intervals. This is just given by supersymmetry constraints. but the H functions can have this behavior. Basically, this choice is telling us that, for instance, in H4, it starts at 0 here, and then it will go again to 0 at some point in the row interval. And this is telling us that the row interval will be of finite size. And this is very important, will be very important later on. But we can say more, because in here, we see this is a piecewise continuous linear function, as can be seen, of course. From here, we are decomposing this. The argument was it is linear, but we can consider this global solution where this is piecewise linear. And we see that something interesting is happening here whenever we have some change in slope, whenever we move through the row interval. And so this might signal the presence of sources that will become very clear later on, but just keep this in mind that in here, what we are basically doing is that, as I said, the solution is parameterized in terms of these three functions. But in here, we are allowing the derivatives of the H functions to change whenever we move from an interval, from one interval to the other. But we need to require that the other pieces of the solutions are continuous. So if you plot the derivatives of the functions H, you will see that the behavior is just a step function. So
can I ask, so you said H8 had something to do with the Romance mass, or
yeah,
what was the connection?
Yeah, exactly. Here is the
the derivative. So that's why it needs to be constant.
Well, roughly what we are doing here is we are allowing the fluxes to change whenever, I mean, right. If you see the NS sector, it doesn't depend on the derivatives of the H functions. But the Ramon sector will depend on that. And basically, you will find sources whenever you have these discontinuities on the derivatives.
Right.
So, yeah, this is what we see from here. And also the presence of these sources that we are seeing here is telling us that the row interval is divided into cells of length 2π. And just to keep these numbers in mind, for instance, if you compute the derivative of the first two consecutive elements, you will see that the first minus the second will be nu0 minus nu1. And just to keep that number in mind, we have more, but these together with the constants here will have some precise physical meaning that will become clear later on. Yeah.
What is the dilaton doing?
The dilaton, well, the dilaton is continuous. It's not doing anything. It's just like.
Oh, okay. Oh, but it is divided by H8, so yeah, it also changes behavior.
No. What I'm imposing here is that the derivatives of the functions change, but not the functions itself. So after
you impose, but the derivative of the dilaton also will be changing.
No. Maybe I should explain this. The only thing that I'm imposing I'm allowing them to change is this HA and H4. They can change whenever we move, because later on we will see that because we are allowing them to change, that's why we are having this change in slope. And this will tell us, or this will signal the presence of sources. But whenever you have to impose conditions, because the NS sector, the metric, the dilaton, and the NS3 flux, they have to be continuous through all the intervals. And whenever you impose that condition, then you will find that you will find conditions on the constants that appear here in the piecewise linear solution. But the NS sector must be continuous through the intervals. But you can,
Yeah, I see it's continuous, but it does look, because it depends on H4 over H8. So it looks like it's gonna have the derivative might have some.
Well, no, really nothing happens, because as I said, the derivatives change. The derivatives of the H functions, they will change. But you can take the dilaton, for instance. You can take the dilaton in this, let's say, in this interval, and then compare it with the dilaton in the second interval and impose continuity, and you will find that continuity is ensured if you impose these conditions.
Yeah, no, I see the continuity is not the same as the derivative change.
Okay, yeah, but this will not cause any problem to the solution.
Okay.
Everything will be well defined. The dilaton will not blow up at some point, so the behavior in there is well defined. So the only possible problem you might have is because you will have sources there, but even that will not be a problem whenever you separate them properly. Yeah, this is more or less all what I have to say about the solutions. So now, yeah, I repeat, this will be continuous and will not give any problem at all. So now, to discuss the deformation of these solutions, basically the method I'll apply here is you can basically apply this method to any kind of solution that enjoys two U1 isometries, which means that you have a two torus on the geometry. And yeah, you can imagine this thing like taking the 10-dimensional theory, reducing to 8 dimensions, and then you will know that you will have SL2R times SL2R symmetry. One acts geometrically, and the other one acts non-trivially on this tau parameter. Where the tau parameter in this case for the two torus is just the component of the B field along the two torus and the volume of the two torus. And interestingly, this has an analogy with T-duality because yeah, all we have to do is just to pick the two torus. It is in this case is parameterized by these two coordinates here. And the thing that we have to do is just to apply a T-duality on the first, shift with parameter lambda in the second, and then T-dualize back. And this procedure ensures that if you start with a solution, then you will end up with another solution parameterized by this lambda parameter here. And yeah, the only thing we have to do in this case is like, okay, we will apply this deformation to the background. So whether we have to select the two torus directions along which we can deform these solutions. And so just to recall, this is the way the solutions look like. And indeed, in this case, for instance, we have at least two options for the two torus. For instance, we can take the U1 inside S2, and we can take the other U1 inside the T4, or basically just take the T2 inside the T4. And for now on, I will just focus on the second option, which is this one. And then, yeah, after applying this TST transformation, then you will obtain this solution, which doesn't look that bad. This is basically the transverse space, which is like an spectator space, the part of the two torus that was deformed. And it's very typical from these configurations that you get a component of the B field along the two torus, and it's this one. And also you will have non-trivial deformations for the rest of the fields, where of course this background is such that whenever you turn off the parameter lambda equals 0, G will be equals 1, and then you recover the original solution. Yeah, it is simple to prove that this solution will be a solution of massive type 2A supergravity. Once again, whenever you impose these conditions on the three functions appearing here, once again, away from localized sources.
Yeah, can I ask about this T-duality again? So if you choose the first option, so yeah, to take one of the circles on the S2 and the other on the T4, so which one are you T-dualizing on? Which is the phi 1, so to speak?
You mean
which one is shifting and which one is
okay? That is not important, because at the end of the day, if you apply, for instance, you can apply T-duality on the U1 in here and do the shift in the second, but you can prove that you will obtain the same background if you just change the way you apply this transformation. Okay. So so yeah, in here we focus here. We found the solution. The other one, later on, will become clear why I will not discuss that solution. But now one might wonder if this applies to 10-dimensional solution. One might wonder if this can go through to 11-dimensional ones, and the answer is yes. We can take solutions with a 3 torus on the geometry, and the idea is the same. You have your 11-dimensional solution, you compactify on T3, and then you will have SL3R times SL2R symmetries. SL3R acts geometrically, and the SL2R acts, as we know, on the Keller parameter of the 3 torus. And so all we have to do in this case is to start with an appropriate KK ansatz, that is given by this expression, where this part of the metric is just the the 8-dimensional transverse metric to the 3 torus. This is the 3 torus part, where of course the A and B indices run along the 3 torus directions. And we decompose the gauge field accordingly. And I'll explain here the notation. Here C, parenthesis 0 means that this field has no legs on the 8-dimensional transverse space of the 3 torus, or has all legs along the 3 torus, which is obvious from here. The second one, the same, it has one leg in the 8-dimensional space, 2 on the 2 torus, etc. And then this one is just where we have all legs on the 8-dimensional space. And in here, the differentials, the notation I've been using here is just the typical differentials, but we allow a non-trivial fibering over the transverse 8-dimensional space. Yeah, in this case, we know how to act on the Keller parameter. It will act on the usual way. In this case, it will be in terms of C0, this field here, and the volume of the 3 torus that appear here in the metric. Yeah, in here, regardless that we don't have a T-duality-like procedure in which we can apply the TST transformation as I described before, we can just transform the solution using SL2R. And the way we do that is by organizing the fields according to the indices they have in the transverse space. For instance, these in blue, they are like vectors with respect to the 8-dimensional space. Also, you can have the G mu, you can put them together in a doublet and just act with the element of SL2R, the same one that gives you the transformation of this Keller parameter. This one is not going alone. You can take the total derivative of this to find a Forfang flux, and the Hodge dual of this in 8 dimensions together with the flux itself will form a doublet, and you will find the transformation of all the fields here. And basically the solution will look like this, with of course with some prime quantities here. The only thing you have to extract them from this transformation here and the transformation that we know from these parameters, the Keller parameter of the 3 torus. So yeah, in this case, the solutions I'll discuss, or the ones that we will take as seed solutions, are just the uplift of the solutions I discussed in 10 dimensions. But remember, in order to do that, we have to set to 0 the Romance mass. And for that, if you remember, these solutions do have the 10-dimensional solutions are in massive type 2A, so we have to go to the massless limit in which we set this to 0, which means HA is a constant. And then I will choose that constant to be K. We use the usual Kaluza-Klein ansatz. We put the solution in 11 dimensions. And that defines a whole family of AdS3 solutions preserving 0-4 supersymmetry in 11 dimensions, and was formed by Yolanda Lozano and collaborators. And basically the solution looks almost the same as the 10-dimensional one of up to this factor here that contains information of the dilaton. And we see here that the S2 that we have in 10 dimensions together with the 11-dimensional coordinate form an S3. But it's an S3 mod by ZK, where this K parameter is the constant value of the H function that allows us to go from type 2A to 11 dimensions after uplifting the solution. And so once again, the thing that, of course, one can prove that these solutions are solutions after we impose, once again, that these 3 functions are order 1 polynomials. And the only thing we have to do, once again, regardless that we don't have this T-duality analog, we just have to pick the 3 torus on the geometry. And if we don't consider the U1 inside the S2, we have at least 2 options in here, because once again, I can take the 3 torus just inside the T4 in this part of the geometry, and I can take 2 torus inside the T4 and the 11-dimensional coordinate. Those are basically at least the 2 options that we have. And then for the first case, whenever we consider the 11-dimensional coordinate as part of the 3 torus, then we generate this solution. Where on purpose in here, I choose the same G as in the 10-dimensional solutions, because one can prove indeed that this solution is the uplift of the massless limit of the solution I found in type 2A. And if I'm not wrong, these solutions...
Salomon?
Yeah.
Salomon? Is K an integer?
No, it's not. It's just a constant. I mean, it's the only requirement that we impose is we need, remember here, we need this quantity to be constant because we need to take tie to A, not massive tie to A, in such a way that we can put a solution on 11 dimensions. But we are not imposing any other constraint on that. Then whenever you find the solution, of course, this is, you find that the K parameter is just given. I mean, that will be the orbifolding parameter on the tree sphere, but it's not restricted.
Okay, but I only understand what set K means is if it's the cyclic group and K is an integer, positive.
Okay, Joe. Okay, yeah, but in principle it is not. It is just you manage to write down the metric in this form, and then that is the metric of the S3 mod.
Oh, that's what I mean. Okay, so there can be a deficit angle.
Exactly. Yeah. So okay. Sorry. This is for, as I was saying, that this solution here is I think is what is called as the TST analog in 11 dimensions, because basically this solution is what you typically do is to take the solution in a solution in 11 dimensions, then you go down to 10, you apply TST there, and then you go again to 11. If I'm not wrong, that's what is called the TST in 11 dimensions. And that the reason is because we are taking this set parameter as part of the tree torus, but we can, for the second solution or the second option we have, whenever we don't consider the set coordinate, and we generate this background. And of course, this looks a little bit more messy. It's not that messy, just I didn't find the proper way to write it more compactly. But one of the reasons because this second background is more complicated is because to begin with, we have a C0. Remember, C0 was the components of the gauge field along the tree torus. And for this case, we have a non-zero C0, and that's the reason why this background is more complicated to begin with. But you can see easily that if you set the C0 to 0, then basically this cold G would look too much like the G we found in 11 dimensions. So this background will not be equivalent to this one. And this, of course, we can take these two solutions and with these definitions, of course, and prove that these solutions are solutions on 11 dimensional supergravity. Once again, where these trees, the U, H, sorry, in this case, because I said HA to be constant in here, there is a typo because HA by default is constant. So it satisfies this condition by default, and then U and H4 must be, the second derivatives must be 0.
Where did U come from?
Sorry?
Where did U come from?
The U. What do you mean, where did it came from?
Yeah, when did that appear? Because you didn't have that in 10 dimensions, did you?
Yeah, we did. It's here, the function, look. I mean, it's everywhere here. I mean,
okay.
Here I just use this notation because F is containing derivatives and also U is somewhere here. So we don't have to have more.
3. I see, yeah, it's the warping in front of the...
Yeah, exactly, it's
okay,
here.
I see.
Yeah. Okay, yeah, now this is all about the deformations. This is all the thing I will say about the deformations. And now I'm gonna discuss the observables that can characterize these solutions. And the first one I'll discuss is the quantized charges, or these roughly will tell us which kind of branes are allowed to exist in our configuration after we deform the solution. So in this case, what we have to do is to study the quantization of the page fluxes. So we have to ensure that this quantity is an integer in order for us to have the corresponding brane in the background. So I'll explain the notation here. This is just the magnetic component of the page flux that is just given by this expression. Is the usual Ramon flux. In this case, we have an extra term that contains the B field. And yeah, we have, in order to achieve the quantization of these page flux, we have to integrate over a non-trivial cycle. And if we achieve that, then we can more or less say which kind of brain we will have in our configuration. For the backgrounds of for the metrics that that I just described, one can choose these non-trivial cycles to be these ones. Basically, the first line corresponds to the cycles that we had before we defined the geometry, and the second line are the ones that we can consider after we define the geometry. So from this analysis, it seems we'll have new objects after we define the solution. And yeah, as if you remember, we said that the rho interval was divided into cells of length 2 pi. And then in here, I would just focus on the quantization of these fluxes on this interval in particular. And yeah, after applying this formula with this, of course, we have to go to study the Ramon fluxes, construct the page fluxes, and then integrate them over these cycles. We find that the charges for the corresponding branes are given by these expressions. And in principle, these are all the allowed branes that we have in our configuration. But of course, if they are allowed, we have to ensure that these numbers are integers, because if we don't ensure a proper quantization of the fluxes for these branes, then those branes mean the bottom line will be that those branes are not allowed in our configuration. So as I said before, the constants that appear in the definition of the piecewise linear functions, they are not totally arbitrary because they will define the quantization of these fluxes. Then they have to be integers, the same for all these numbers. But we see that after the deformation, a new condition appears, because basically we know that this one is integer, this one is integer, but lambda now enters in the quantization condition. So if we want these branes to exist in the background, we have to ensure that this is an integer, and that can be done if we consider that lambda is a rational number, such that the number of these branes, for instance, this beta k will be related to the default branes. This is an integer, but this integer after the deformation needs to be a multiple of n, for instance, if we impose that this gamma is rational. And then that is the condition we have to impose in this case for these branes to exist. Yeah, in this case, we have a single NS5 brane in every row interval. And we will have a number p plus 1 NS5 branes whenever we integrate the flux of the H3 flux over the whole row interval. Something interesting here to notice is, for instance, yes, I was saying before that it's important to consider this row interval to be of finite size, and here is one of the reasons why, because whenever we integrate this H3 over this flux, from here we will get the charge of the NS5 branes. And for instance, if we integrate over rho, and if rho is not bounded, then we will have an infinite number of them. There are models, of course, that they might have an infinite number of NS5 branes, but typically the field theory associated to those solutions is not well defined. So in this case, to have a well-defined CFT, or having in the back of your mind that we will go towards a well-defined CFT, then we impose this rho to be to be finite. And then, as I said before, we ensure that by imposing this behavior of the piecewise linear function. And then in that way, we can achieve that the total number of the NS5 branes is p plus 1. And so what is happening here, as I discussed, is just in one interval. And basically what we are seeing is that we have between two consecutive NS5 branes, that in here are the vertical lines. This is one NS5 brane, the other. This configuration is happening between two NS5 branes. And what happened here is that we have DA branes, we have D4 branes, we have new D6 prime branes, and these other branes that we have here. These, of course, have to be understood as a stack of branes, because remember that this is a number that we have to impose to be very large, because yeah, now we'll explain that in a better way. So yeah, now that we know which kind of D branes we have in our configuration, one can wonder which kind of branes they are. I mean, if they are color branes or flavor branes. And so in order to answer that question, one can study the violation of the Bianchi identity. because basically if we have the violation of the Bianchi identity will tell us that will signal the presence of a source for the corresponding brane. And so if you remember the behavior of the as I emphasize, the behavior of the derivatives of the functions, they were like step. So whenever we have a change, we will have a delta there. And if you go directly to compute the violation of the Bianchi identities, you will realize that this is given by the second derivative of h, which is given by this expression. And basically this number here is roughly telling us the number of the corresponding d-brane. And also that the branes will be located at rho equals 2 pi k. This is all what we can get from here. So the only terms that will allow for violation of the Bianchi identity are second derivatives of h. That's why I was allowing the h function to change, because remember, this is basically the derivative in one interval minus the derivative of the other interval. And so if we don't allow that, basically we will not have sources. And if you remember, this nu0 minus nu1 term is just the number of branes, of the flavor branes in the very first interval. That's why I said it will have a precise physical meaning. So we can have in here violation of the Bianchi identity whenever we have, as I said, second derivatives of h, and this is possible just for the two functions h4 and ha. And so that means whenever we do the computations carefully for all the fluxes in the solution, we'll have just sources for D4 and D8 branes, and also D6 prime branes that were the ones that appeared after we deformed the backgrounds. And yeah, for the rest of the branes, because these will the right-hand side will be 0, then they will be color branes. Then in this way, we can classify the branes in terms of what they are, flavor branes and the ones that are color branes. And basically, all what I have said, it can be more or less summarized in this table here, where we have all sort of branes that we have found. And in here, the bullets correspond to the work volume directions of the corresponding d-brane. The dots are the transverse directions. And this is the number of branes in the corresponding k interval. And the claiming here at this point is that this complicated intersection of branes will give rise to the solutions I have just found, the gamma deformed solutions or the lambda deformed solutions. And in order to leave the idea more clear in here, I'll take the avatar example in AdS3 that is whenever we consider a flat space and we put a stack of D3 branes in flat space. And then, of course, the D3 branes will backreact flat space. You take the near horizon limit and you will find AdS5 times S5. So the claiming here is exactly the same, that we have to consider this complicated brane intersection. And after we take the near horizon limit of this complicated intersection, we will obtain the AdS3 solutions I just found by the deformation. Where of course these branes will be sitting in a more complicated space. This is not flat space. These are all the coordinates on which we have to put the branes. In principle, we have a Calabi-Yau space and we have some mesio-3 symmetries, etc. So yeah, it will be a little bit more complicated, but the argument is that one. This will be the brane intersection we have to consider before to take the near horizon limit, and then after the near horizon, we will generate the solutions I just found by these deformations. And yeah, now that we know what is the brane, more or less the brane configuration that generates our solution, then I'll discuss another observable. And if you notice, or mostly the title of the talk was that I will be considering marginal deformation of the CFT. And typically what you do whenever you consider a well-known pair, you know a supergravity background and you know that it has some well-known CFT. And then you deform the background and you wonder what happens to the CFT in this case. And then for this kind of deformations, the claim is that they correspond to marginal deformations, which means something in the CFT. And one of the first things you might see that this is, of course, I'll say better backgrounds, dual to marginal deformations of the CFT, is that the AdS factor is there. It was an spectator factor, so you can easily see that the deformation you do in the supergravity background, if you preserve the AdS, then it would correspond to a marginal deformation. But we can prove that fact in a non-trivial way by analyzing the central charge of the solution. And the claim is that if you perform a marginal deformation on the CFT, then the central charge will not change. That is basically the claim. And so in here, all the thing we have to do is to compute the holographic central charge and prove that basically it hasn't changed after we deform the solutions. And yeah, the idea behind this thing is that it's a very well-known result that the central charge for CFT2 is just inverse to the Newton constant in 3 dimensions. And there is a relation between Newton constant in 3 dimensions and the volume of the internal space. Internal in this case is the transverse to AdS3. So the Newton constant in 3 dimensions is inverse to the volume of the 7-dimensional space. And then as such, the central charge will be proportional to the volume of the internal 7-dimensional space. And then the only thing we have to prove at the end of the day is that the volume of the internal space hasn't changed. And with that, we will be able to prove that the central charge hasn't changed from the holographic computation, of course. And so, yeah, this is basically the idea behind. And if we go to formulas, we can take a background, in this case, parameterized by this metric, where in this case, this is Minkowski 1, D, and this is the R direction that together with Minkowski 1, D will form AdS space. But in here, it is a little bit more complicated because this formula is allowing for some kind of RG flow. We have non-trivial warpings here that also they can depend on the internal internal space. And the formula basically for the central charge is given by this expression where we have constants here and there. But important information is here because this encodes the information of the volume of the internal space. And in here we have the stringy volume. And I'm calling it the stringy because we have a non-trivial dilaton here. The usual volume is just this, the square root of the determinant, but we have a non-trivial dilaton. So that's why, because we are in stream frame. So all the thing we have to do is just to prove that this thing is invariant under the transformation. And so in order to achieve that, the only thing we have to do is just to write properly the fields in the solutions in such a way that, for instance, we can write down the dilaton before we deform the solutions in terms of the dilaton, after we deform in terms of the one before we deform, and the same for the metrical on the 2 torus. And yeah, all the thing we have to do, regardless the other terms here in the formula, is to prove that this quantity hasn't changed, And yeah, we do that, and indeed, you can prove easily that these factors, they do cancel whenever you compute this quantity, and then you can prove that the central charge before and after the transformation remains the same. And so this is a non-trivial proof that, of course, these backgrounds are dual to marginal deformations. And also the same thing will go through for the 11-dimensional solutions. The only thing, of course, you have to modify in this formula is that, of course, we don't have dilaton terms in 11 dimensions, but you can redefine this quantity that is given by this quantity down here. And then following the same thing as here, writing the fields before and after the transformation, you can prove that indeed the central charge before and after the transformation is exactly the same. So the backgrounds obtained will be backgrounds dual to marginal deformation to do these solutions.
So this just follows from the general fact that TST transformations preserve the combination of e to the -2 times the dilaton times the square root of the determinant of the metric.
Yeah,
What
basically.
you would call the generalized dilaton in double field theory.
Yeah, exactly. I mean, yeah, it's basically that combination you said. I mean, it's because basically the the volume, as I said, it just involves this thing, and you know this quantity remains invariant. So that is
it's
basically
invariant under T duality, and so if you add a shift, then doesn't change anything. So
yeah, exactly. So yeah, that's the whenever you go to those to see from that point of view, is very, very simple to see even without writing these equations here. Okay, so now I'll move to the issue of the supersymmetries preserved, and then yeah, and here we know that or the question to answer is like we started with a solution that preserves 0-4 supersymmetry. And so we wonder how many of these supersymmetries were preserved after we transfer the solution. And one way, the way that I will study here is just to know the precise form of the spinor, because from there we will see which components of the spinor will be preserved. And of course, the construction of the spinor was obtained in the original work, but was a little bit different, because in there they just gave the spinor and used this G-structure formalism to construct the solution that I just presented before. In here I will proceed the other way around, in which I will take the solutions and obtain the form of the spinor of the solution. And basically the thing we have to do is just to start with, we are I will just discuss only the case of type 2 supergravity, because in 11-dimensional solutions will go through the same analysis. And yeah, we are in type 2A supergravity, so we have to consider these two spinors, which are Majorana-Baird spinors with different opposite chirality. In this case, this spinor here is an AdS3 spinor, will not be important because as we prove this transformation, for that transformation AdS3 space is untouched. And then we have a 7-dimensional spinor, which we will try to obtain the form of this 7-dimensional spinor, and this vector in both cases is just taking care of chirality in 10 dimensions. So yeah, as I said, the thing we have to do just to take the supersymmetry variations, where this slash notation here means usual contraction with gamma matrices. This capital gamma is refers to 10-dimensional gamma matrices. And sigma here are just the usual Pauli matrices. So all the thing we have to do, once again, to take the solutions, plug them here, set the supersymmetry variations to 0, and then after doing that, we'll find that the form of the spinor is given by this expression here. This looks very simple for all the symmetry we impose on the solution, where this Chi0 parameter, Chi0 spinor, is a constant spinor satisfying these two projection conditions. And each of these projection conditions reduce supersymmetry by half. And then this is a quarter BPS solution, which is another way to say that we are preserving 0-4 supersymmetry. And yeah, now one can study the preservation of supersymmetry, but before to go there, notice that this 7-dimensional spinor splits in a C-Schul in terms of an S2 part and the 5-dimensional part. But the 5-dimensional part just depends on the raw coordinate, because we impose to these solutions to have the Calabi-Yau symmetry. So the spinor must be covariantly constant along the T4. So, and from here we see that that's the case. And so this 7-dimensional spinor can be split into the spinor on the S2 times the spinor on the M5, as we were expecting. I mean, we were expecting that for the form of the solutions we impose on the solution itself. So yeah, the way to more or less to study the preservation of supersymmetry is because the procedure in 10 dimensions involves T-duality. One can study the preservation of supersymmetry using this criteria of the Cosman-Lie derivative, in which these criteria tell us that the action of the Cosman-Lie derivative along the Kirin spinor that we use to generate, that generates this isometry along which we apply the T-duality, acting on the spinor should be 0, which in an appropriate frame for T-duality implies the independence on the spinor on that coordinate. And a second condition appears because we are applying this shift of parameter lambda on the spinor, and the spinor has to satisfy this global periodicity. And so the simpler way to achieve this is to impose that once again the spinor doesn't depend on that second coordinate that we used to shift. And so a bottom line is that the spinors have to be independent on both coordinates, or both of the two T2 coordinates that we use to perform this transformation, or say in other words, that the U1 times U1 symmetries commute with supersymmetry. So in that way, we ensure supersymmetry is preserved. And for instance, for the first solution I consider, in which I was touching the U1 inside S2, because we have a non-trivial dependence on this coordinate here, one can prove that indeed after the first duality, you will break supersymmetry. So regardless that this is a good solution, it's a solution of supergravity, it will not preserve supersymmetry. So that's why we didn't consider it. And for the second case in which we have the T4, of course, T4 has not, I mean, the T4 coordinate doesn't appear here in the spinor, so we ensure supersymmetry is preserved following this criteria here. But indeed, we can prove that more directly because we can consider these, the supersymmetry variations, put the deformed solution, and then we will find that the supersymmetry transformation of the D Latino and the gravitino, they are not independent of the undeformed ones. They are related in this way. So you can see that it was like deposed like a rotation. But these ones are unchanged, where once again, 1 and 2 refers to the chirality of the spinors. And this is true provided you identify the spinors of the solution in this way. So once again, the conclusion is that after we apply this transformation, basically the spinor gets a phase or gets a rotation due to the transformation. And of course, if we turn off here the parameter, we recover the spectral relation between the spinor. Basically, they will be the same. And from here, of course, it's very simple to see that if we started with one solution that is supersymmetric, then the solution generated will be supersymmetric. And this will help us because one might wonder what is the fate of the G structure of these solutions after we deform the solution. And if you remember, the classification of these backgrounds was obtained, as I said before, by imposing that the 5-dimensional space enjoys an SU2 structure. And one can study what happens with that SU2 structure after we deform the solution. And yeah, the way we will do that is because we know the way the deformation acted on the spinor. But in general, to say that an spinor preserves, I mean, is characterized by an SU2 structure on M5 if we can write down this 5-dimensional spinor in this way, where here A and B are just complex numbers.
Is G SU2?
G, yeah, the structure group is SU2. I mean, these solutions, the ones that I've been describing, the seed ones they do enjoy an SU2 structure to begin with. I mean, the classification these people found was we impose an SU2 structure on M5 and then we work with that. And then in here, I wonder what happened with that G structure after we deformed the solution, because basically I found a non-trivial relation between the spinors after we deformed the solution. So yeah, because M5 supports an SU2 structure, then that means that the spinor in a common basis can be written in this form. Once again, A and B are complex coefficients. This is the conjugate to the spinor eta. And yeah, all we have to do is to see if we can write down the spinor after we deform the solutions in terms of this basis or not. And remember, in here, I just wrote down this condition for the 7-dimensional spinor, but we can split the 7-dimensional one in terms of as a 2 + 5 splitting. And then this relation in 5 dimensions look like this, where these gamma matrices here, they were 7-dimensional. Right now, these are 5-dimensional. And then in order to see exactly the relation, we have to find the way these gamma matrices act on the 5-dimensional spinor, but we can use the relations I found here to induce the form. These spinors act on the 7-piece gamma matrices act on the spinor. And then at the end of the day, we find that the precise relation between the spinor before and after the deformation is this one. And you can easily see from this expression that this looks very much like this one. Of course, this B term here for the class 1 solutions that I've been describing is B equals 0. And this A that apparently will be a phase in front of the spinor is 1 for the class 1, for the seed solutions. So one might wonder what happens after we deform them. And then what happens is that it acquires a new phase in terms of the parameter gamma. And yeah, the thing is that we started with an SU2 structure and then we ended up with an SU2 structure, but this phase is point dependent. So which means we are getting a dynamical SU2 structure just because this phase depends from point to point along the rho interval. And this is given because we have non-trivial warping, basically. If you take, this can be taken as a generic thing, you take a solution on which the two torus has a non-trivial warping, and it is the form, the spinor is the form basically as in this way, then you ensure that if you started with a, let's say, SU2 structure, then you will end up with a dynamical SU2 structure, and the dynamics of this structure will be given basically for the, we associated to the warping factor in front of the two torus. So yeah, bottom line is we generate a solution with a dynamical SU2 structure, and up to here, techniques generating solutions are very powerful in this sense, because of course the classifications scheme, they have to at some point impose some conditions on, put some topological constraints like to impose the SU2 structure on M5 in order to make progress to find a complete classification of solutions. And these techniques generating solutions allow you to find sometimes solutions that are out of the presently known classifications of supergravity backgrounds. And this is basically an example of that. So yeah, I don't know how much time more I can take. I think I'm over the limit.
No, it's fine. You can talk as much as you want.
Okay. The last part, I think, is just, this is some work in progress. So I will say quite a few things, but this involves I mean, this part up to now was like the geometric part of the work. So right now, I'll discuss a little bit about towards the CFT realization of the meaning of these deformations on the CFT. And yeah, before I did present one of these intervals. Remember, we were discussing what was the brane content on one interval. And here you got the whole picture. Remember that the rho interval is composed of P+1 branes, which means P+1 NS5 brane, which means we have P intervals. And then on each of these intervals, we have this brane configuration here. Yeah, of course, we have in here, this is just the brane configuration for the seed solutions. And of course, we have to add here the D6 prime branes and the D4 prime branes that I found before. Sorry, that we found after the deformation. But yeah, this is the whole picture. And do you remember that we said that the D4s and the D8 branes, they were flavor branes because they are actual branes in the configuration. The color branes, they are not there anymore in the solution because they were dissolved into fluxes. It's like the AdS3 times S5 case. You have a 5-form flux that you can integrate and obtain a number of D3 branes, but that doesn't mean that the D3 branes are there in the configuration. They are just dissolved into fluxes. That happens for all the color branes in this Hannany-Witten brane setup, but not for the flavor branes because the branes are even there after we took the near horizon limit. So we have to prove that those branes, because they are in the background, they do define a supersymmetric embedding. And then for the original branes, it was proven in the original reference, and they define a supersymmetric embedding, provided you turn on a work volume flux on the work volume of these DA or D4 branes, or what is the same, you impose large gauge transformations anytime you cross the log key of the NS5 branes. And I didn't mention that because it wasn't too important for the discussion here, but I've been working mostly with the second option. And roughly this is ensuring that whenever you go from one interval to the other, you are just having one NS5 brane in here. So you start here, you move, and then you have one NS5 brane, you apply large gauge transformation, such a way that you just have one, then you move, etc. So, but the turning on a world volume flux and applying large gauge transformations is totally equivalent. Also, that ensures that the modify Bianchi identities, because we have sources, they are solved, etc. Yeah, but if you remember, after the deformation, we have extra objects. We found D6 prime branes and D4 prime branes. That I said before that the D6 prime branes, they are flavor branes, so we have to be careful that they do define a supersymmetric embedding. And then the thing we have to do is just to take the usual action for the D brane. Yeah, try to prove if they are or not supersymmetric embeddings. And then indeed for this solution, you can prove that they do define a supersymmetric embedding, provided you turn on a world volume flux along the two torus direction. And this basically means that we will have a D6 prime D4 bound state. And this can also be seen because, yeah, mostly because whenever you take this Besumino part of the action here, you will see that the coupling of the D6 branes is 0. And then the non-zero term in here will be just the coupling of the D4 brane, because the term that will survive here will be sort of a C phi, that is the C potential associated to a D4 brane couples to an F6. And then this is basically in this formula is associated to a non-zero C phi. And then C phi, which this world volume will be the non-zero term in here. And that means that there is some charge of D4 brane induced in the world volume of these D6 branes, or say in other words, this is basically what is known as the Myers dielectric effect, in which the D4 branes blow up into form the D6 branes and the blowing up is ensured just because you have a non-zero world volume flux along the two torus. And yeah, the same thing happens for the lower dimensional branes, that also we found these D6, but we also found D4 prime branes. But following an argument like this one, you can prove that the D4 will form a bond state together with D2 branes. And then, yeah, following this argument, you will be needing to turn on a world volume flux. They will be supersymmetric embeddings. So the same conclusion can be reached. So it seems that we will end up with the same branes. That's what I was saying, that we generate new branes, and we didn't, but well, we did, but we are seeing that they are part of a bound state. I mean, D6 with D4s and D4s with D2. And actually, if you study the supersymmetric, the embeddings of the seed branes, the D4s, and the D2s that were there before the deformation, you can prove that they disappear basically. They are not, they will not define supersymmetric embeddings anymore, because you have to, for instance, for the D4, you have to move the D brane to a point in which the two torus shrinks to a 0 size. But that is not possible because the D4s are flavor branes. They are located at rho equals 2 pi k. And you cannot move them unless at 2 pi k you impose that the two torus shrinks to 0 size. You will achieve that, but it seems that is not possible. So you basically, the D4, the seed D4 and the seed D2, they are gone. But if you look carefully, you say, oh, they are not really gone, because they will appear as a bound state of D6 branes, and the D2s will appear as a bound state together with D4 branes. And yeah, one can also do more at this point. Like for instance, if we study this DBI plus Besumino action for a D6 brane, and we allow the brane to fluctuate, say to prove the transverse space to the brane, then you will see after integrating over in an appropriate embedding, you will see that after integrating over the two torus coordinates, then you will see that the new D4 brane, the one in here, because the D4 brane will have these work volume coordinates that are exactly the same as the D4 we considered before the deformation. But the thing will be that D4 brane, because the gamma parameter, remember that the gamma or the delta lambda parameter, in order for this D6 to exist, needs to be rational. We have to choose a proper value that in this case for m equals 1, I consider 1 over n. This, whenever we choose this parameter, this will change. It will have an impact on the new coordinates because the story is as follows. You have a coordinate that was transverse to the brane. And then after you apply TST, this new coordinate became a coordinate along the work volume of the brane. That is what is here. And then that coordinate now defines a Wilson line for the brane. So in that case, for a specific embedding of the brane, whenever you allow all these fluctuations of the brane, you will see after, once again, integrating over the two torus, that the work volume flux that was the scalar before will be related to a new coordinate, but that new coordinate will have a different periodicity, and the different periodicity comes by this, whenever we choose this lambda to be 1 over n. And bottom line is that the D4 brane that we are getting after the bound state of D6 prime D4 apparently will be the same as the one before we took with the front diagram, but it's not, because the effect of the deformation was to change the periodicity in this way. And then actually that D4 brane, because the branes are basically proving the transverse space, that new D4 brane is not seeing anymore T2, but an orbifold of T2. So that will be somehow the way we will realize how because D branes are proving, the modular space of these D branes are like, the freedom they do have to move in the transverse space. And then after this analysis, one can prove that an orbifold of this form will appear on the T2. And that would be more or less the effect of deforming, how the effect of the deformation will appear in these embeddings. And yeah, one can say more. And the first thing we have, of course, this is like we are going to the CFT. We have to study this effect on the CFT. And I think I have taken a lot of time, but I will just conclude with the last thing in which here, the way we engineer the CFT by knowing the Hannany-Witten brane setup. So as I said before, we can basically summarize all what I have said up to now. This was just in order to see which branes were allowed in the configurations and which ones they were not. And so, but by looking at the Hannany-Witten brane setup, one can more or less engineer the quantum field theory. And I need to emphasize that this will be a quantum field theory. It's not a CFT, because remember that this brane setup is engineered with the information of the UV theory, because remember that I said that after taking the near horizon, we are going to the infrared, and then in there we compare with the AdS background. But this theory that we will extract from here will be the UV theory. That of course the argument is that after that the UV will flow to an infrared fixed point, and then in there we will compare with the supergravity solution. So yeah, all the thing we have to do is more or less to read off what information is in this Hannany-Witten brane setup. And yeah, with the experience we have from this avatar example that I've been taking, is like in the solution of AdS 5 times S5, we know that solution is dual to n equals 4 super Young mills with UN gauge group. And the UN gauge group appears basically because we have this stack of branes, and we can consider all the possible massless modes that are between all the strings that are between all the possible n strings that compose the stack, because the branes are on top of each other. Then you can consider all the strings, in that stack, and you will conclude you have a UN gauge group. The same will happen here, and that will happen for the color branes. So if we take that into account, we will have in this case 2 gauge groups corresponding to the, in this case, the D6 and the D2s. We found that they were color branes. Then to begin with, we will have 2 gauge groups. And we will have in this case 2 flavor groups. And more or less the information, of course, we'll have this is in one interval, but we have more intervals. But the information of that will be quantum field theory, can be encoded in what is known as a quiver. The thing that I said before is just given by this configuration here. But this, in this notation, this quiver is, we have a stack of branes that we generate a gauge group. So gauge groups are represented by these nodes. The second gauge group is the second node, and for the corresponding in the second segment, we will have once again other gauge group and etc. And the boxes in here are just referring to flavor branes. But of course, we have to connect to furnish the quiver properly. And the way we do is to use this well-known fact that the strings between the corresponding branes are in one-to-one correspondence with the supersymmetric multiplets of the 2D CFT. And then all we have to do is to study in this case, the supersymmetric multiplets of the 0,4 CFT, which, in order to understand which kind of fields will be furnished in this quiver. And those fields, and as I wrote in here, corresponds, for instance, we have these were the flavor branes, the DA flavor branes. We'll have strings that go between this stack and this. And this will correspond, or it will be in one-to-one correspondence with the fields that will connect this flavor box and the gauge node. And the same for the rest. We will have strings that go between this stack, and then they will furnish this part of the quiver, etc. Of course, this is just 2 intervals. We will have, remember that the raw interval will consist of P plus 1 NS by brane. So the whole thing will be a quantum field theory having a number of gauge nodes, all them connected by supersymmetric multiplets in an appropriate way, because this quantum field theory has to preserve 0,4 supersymmetry, and also has to cancel anomalies, because 0,4 is a chiral theory, and then we have to be a little bit careful with the cancellation of anomalies. And yeah, this is what we more or less read off from this configuration here. And of course, the effect after we deformed the solution, we found that there is a sort of a orbifolding on the T2 after we deform the solutions. And basically the orbifolding will be to pick one of these gauge nodes, and the same will be true for the flavor ones. But you pick this one color group, and let's say that the range of the gauge group is Kn, and then the effect of the orbifolding is just to split the gauge group into, in this case, K similar components that is in a circle, in such a way that you respect the symmetry of the orbifold. And if this follows, then these quivers will no longer be flat quivers. You will see them like, you see from this perspective, you will see that they are like cylinders, because this orbifolding that we found given to the gamma deformation. This is more or less what will happen in the CFT. So this is, once again, still work in progress. So I hope to report on this soon. And whenever, after that, I can talk more about the details of how this thing is going. So I think I can stop here.
Okay, thank you very much for the nice presentation. So if anyone has any questions or comments, please feel free to unmute.
So maybe I can ask about the supersymmetry analysis. I expect there should be a simpler way to check which supersymmetries are preserved without just like constructing explicitly the killing spinners. There should be just an algebraic condition right on, basically involving the commutation of the isometry that you use with
Well, the
supersymmetries?
yeah, as I said, like the independence basically implies that the U1 times U1 commutes with the with the supersymmetry. So yeah, I'm not. I don't know if that thing exists. This is, of course, the old-fashioned way, I will say, and the toughest. I mean, you have to compute a lot in order for you to prove that it is supersymmetric. But yeah, I mean, there will be another quickest way. Another possible option is to use the formalism of these structures, because in there you will just see the action of this rotation directly on the structures, and then you will, you know, there is there are some equations that the people that constructed the solutions have to be satisfied for supersymmetry to be preserved, and then if you induce the rotation on the spinner, then you can just go and prove that the same conditions will be satisfied. But also another kind of proofs. But I'm just aware of these two ones. I mean, maybe the one you are saying is way easier, and that's all.
I mean, if you think of this as a Young-Baxter deformation, so you can describe this TST transformations also in the language of Young-Baxter deformation.
Sure.
So then you have some specific R matrix, some abelian R matrix that you read off from the TST transformation you have. And then the symmetries preserved by those deformations you can easily find by seeing whether that R matrix which generators it commutes with in your symmetry algebra.
Yeah, well, the related to this Young-Baxter deformation, the thing that I know is that you can, of course, write an expression like this for any kind of Young-Baxter deformation. So, and there is a precise way you find the precise form of the spinor after, in this case, the Young-Baxter deformation. You find basically that in here you will have this, my lambda here will be like the components of the R matrix in the Young-Baxter deformation. So basically is the thing that you get from that analysis, that the spinor will be rotated.
Yeah, you can construct the spinners too. I was saying, just to find out whether supersymmetries are broken or preserved, you just have to compute some commutator of R with the supersymmetry generators.
Yeah, well, okay, even without computing anything, just because the spinor is independent based on Cosman-Lie derivative, and you can say supersymmetry will be preserved for sure. I mean, regarding the preservation of supersymmetry, it would be very simple to prove that the solution do respect supersymmetry. The motivation for this was to check what was happening with the G structure, because regardless that you prove that, yeah, supersymmetry is preserved, that's all. But the hint was like to see what happened with the structure.
Yeah, for that you need to do more work.
Yeah, that was the thing. I mean, other than that, I mean, I could save time saying here it's independent, that's all. The supersymmetry is preserved. But for the G structure, we need to know the precise form between the spinors. That's
okay. Thanks.
Yeah, so any other questions or comments?
So maybe I can ask another question. So you argue that the geometry that you had corresponded to the IR of the field theory you engineered with your brane setup. Can you construct the geometry corresponding to the UV, and can you construct the whole geometry then for interpolating between the UV and the IR?
Well, the thing that you have to do basically is to engineer this configuration, right? I mean, you take a space-time with the given isometries, like the Calabi-Yau ones and the CO3, and then in there you put this stack of branes. I mean, of course, you know the work volume these branes they have to occupy. Then you put that the intersection, you will generate a solution, you solve the equations, and of course you will find the warpings that in the near horizon limit, they have to give you the solution I found here. There are examples in which it has been proven, but for very concrete examples, but for the seed configuration. But of course, you can take this, think hard and compute, and you have to get that solution for sure. From here, you will extract that information, basically.
Okay.
Any more questions or comments? Okay, if not, then I'll thank Salomon once again for the nice presentation.